The kinetic theory of matter um, says an explanation of how particles and matter behave. So everything is made of particles. These particles are called atoms. And kinetic, if you remember, kinetic energy is the energy of motion. So we can assume three things about matter. Number one, all matter is composed of small particles. These particles are atoms and molecules and ions. So the desk in front of you, the computer, the air, your phone, everything is made of atoms. They all combine to form matter. These particles are constantly in motion, constantly in motion. So again, I'm thinking of the desk in front of you that you're sitting at. That the particles inside that desk, even though it looks like they're not moving, those particles are in constant random motion. Random being those particles are moving everywhere they can. Now, the desk particles compared to particles in a pot of boiling water, compared to the particles in the air, they're going to be moving a little bit differently, right? But everything is in random motion. Third, these particles will collide with each other in the walls of their container. If we think of air in the classroom, that those particles are moving until they hit a wall or till they hit a desk or till they hit each other. If you take some air and put it into a really small little container, well, they're not going to move as far as they would if they had as much space. In a pot of water, if the water is really, really cold, those particles are moving slower, all the way down to where it's ice, right? That's slowing down, slowing down, slowing down. But the ice particles are still moving. But if I start to boil water, those particles start to move a little bit faster. And that has to do with the heat or thermal energy. So those are the three assumptions of the kinetic theory of matter. Now, what does this have to do with the rest of our unit? Well, we get into energy. Energy we talked about before break, the ability to do work, and then kinetic energy was the energy of motion. This is the important part. It's all important, but this is the important part. We have thermal energy. Thermal energy says total kinetic energy of particles. So the example I just talked about with ice. Ice is made up of particles, and those particles are moving. However, those particles are moving pretty slow because they've cooled down, so there's not as much going on. As that ice starts to melt, well, the reason it's melting is because we've put thermal energy into it. And if that thermal energy is being put into it, it's heating up, the particles are moving faster. If I continue to add thermal energy to it, those water molecules go faster and faster and faster and faster until they start boiling. If you've ever seen a pot of boiling water, it seems like those water molecules are going crazy. If it boils long enough, it starts to form water vapor. Water vapor, or basically the gas form of water. Now those particles are moving super fast and they've actually escaped the water. That all has to do with the thermal energy that was placed into that water. It says the temperature is the measure of the amount or average kinetic energy of the particles. The higher the kinetic energy of the particles, the higher the temperature. The SI unit for temperature is a weird one. We don't really use it a whole lot. It's Kelvin, but we're going to use Celsius. If you have absolute zero is 0 degrees Kelvin. That is the first point where particles actually stop moving. That is really, 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 really cold. Really cold. And I'm going to show you that here in a minute. But absolute zero, the particles have stopped moving. We have to know some temperature conversions. So take a look at these formulas here. If you have Fahrenheit temperature, which we use in America, and you want to convert it to Celsius, you are going to take 5/9, 5/9, which is actually 0.59, 5/9, and then you multiply it times the Fahrenheit temperature minus 32. Okay. Excuse me. So you take Fahrenheit temperature minus 32 in the parentheses, multiply it times 5/9, which is, 0.56. You will get the Celsius temperature. To convert from Celsius to Fahrenheit, you take the Celsius temperature times 9/5, or 9/5 is 1.8, so Celsius times 1.8, and then add 32, you will get that conversion. So if you have Celsius, you use this conversion to get it to Fahrenheit. If you have Fahrenheit, use this conversion to get it to Celsius. Be sure to follow the formula. You always do what is inside the parentheses first. So up here I do Fahrenheit minus 32 first times 5/9 or times 0.56. Up here I do Celsius times 9/5 or 1.8, and then I add 32. Kelvin, to convert to Kelvin, I take my Celsius temperature and I add 273. So 0 degrees Celsius is actually 273 Kelvin. So you can see how cold 0 degrees Kelvin is, or absolute zero, which is negative 273 degrees Celsius. That's really stinking cold. This page just has some conversions on it. I want you to practice those, and we'll go over those together in class. Properties of matter. This slide's pretty simple. Properties of matter, the first type of properties are called physical properties. Physical properties of matter are very easy to see. So something that's easy, like the color of something or the shape of something. It could be the mass. It could be, well, look at all these things. That what point, the melting point, or how cold does it have to be for it to melt or warm? Boiling point. Boiling point of water is 100 degrees Celsius. Um, a lot of these things are easy to see. The freezing point of water is 0 degrees Celsius. Density, which we're going to do a couple labs on. Okay. They help us to determine the use of substances, and you can actually identify substances based on their physical properties. So, great example, copper. We've talked about copper before because it has high conductivity. It allows electrons to travel through it. That is a physical property of copper. So we know that, so we put it into our electrical and phone lines. Density is a physical property. We're going to do a lab with density. So if I take the mass of a substance and divide it by its volume, it gives me the density of something. And that's going to determine if that can float or sink, basically. So that's not the only use of it, but think of a piece of styrofoam versus a piece of steel. The piece of steel has a much higher density because there's more mass in the same volume. So if there's more mass in the same volume, the density is much higher. So if I take a block of steel and throw it into the water, it's obviously going to float. If I take a block of styrofoam of the same size, the steel's going to sink. If I take a block of styrofoam of the same size, it's going to float because it has a density lower than water. It's going to stay on top of the water. Okay. I don't want you to worry too much about density right now because we're going to do a couple labs and you're going to identify density of different objects once I'm back in the classroom with you. This has to do with buoyancy, leads to buoyancy. It says the ability of a fluid to exert an upward force on an object immersed in it. Here's all that means. If something is buoyant, it can float. Okay, so its buoyancy allows it to float. And again, I don't want you to bog yourself down right now with density. Physical properties, there you go. Some of them are super easy. Length, color, density, mass, the luster. This has to do with like identifying minerals. Elasticity, the pressure, the volume. These are easy to see, easy to measure. Density, I'm going to come back to that. Flip side of physical properties is chemical properties. Chemical properties are not as easy to observe. A lot of times to see a chemical property, you have to see it change. So you can't just see a chemical property by looking at it. But there has to be some sort of chemical reaction in order to see chemical properties. First one is called reactivity. Its ability to react with other elements, or its flammability or non-flammability. Will it catch on fire? Or its ability to burn. Now, I can't just look at something and say, okay, it has a high flammability. I have to see it burn. So that's why chemical properties are a little harder to see than physical properties. Now, with both physical and chemical properties, we have characteristic properties. These are properties that basically make a substance easy to identify. So Um, Great example, water. I have this substance. I'm not sure what it is. It's odorless. It has no color. How do I find out what it is? Well, I take this substance and I see that it starts to freeze at 0 degrees Celsius and that it starts to boil at 100 degrees Celsius. You will know this as you go through more and more science, but that right there is a dead giveaway that tells you that that's water that you're dealing with because of those properties. So those are its characteristic properties. The ability to freeze at zero, boil at 100 degrees Celsius. That is the only liquid that'll do that. Okay. Other liquids will have other characteristic properties, and we'll talk more about those throughout the year. Here you see a picture of chemical properties, and again, these are a little bit more difficult than our physical properties, because you have to see a change in order to identify it.